Question 11. Use synthetic division to perform the division. First step is to look at our divisor. It's x minus 2. So we need to put a 2 on the outside. And inside we'll put our coefficients. Negative 9, positive 7, negative 5, and a 6. We'll start by dropping the negative 9 and then multiplying. Negative 9 times 2 is negative 18. 7 plus negative 18 is negative 11. 2 times negative 11 is negative 22. Negative 5 plus negative 22 is negative 27. 2 times negative 27 is negative 54. And then we add 6 plus negative 54 is negative 48. This is our remainder. So we can write our solution. Our solution is 1 degree less than our dividend. So we have an x cubed. That means our solution is going to be an x squared. We have negative 9x squared minus 11x minus 27 plus our remainder. Our remainder is negative 48 over our divisor, which is x minus 2. Here is our solution. Question 12, let's factor f of x into linear factors given k is a 0. So they gave us a free 0, so we could use that to divide into our function. 2, 7, negative 87, 108. Now, since the 0 is given to be 4, I know my remainder has to be 0. So let's give it a try. We'll bring down the 2. 4 times 2 is 8. 7 plus 8, that's going to be 15. 4 times 15 is 60. Negative 87 plus 60 is negative 27. And 4 times negative 27 is negative 108. And we do get a remainder of 0. That's what I expect and we should get. Figure out what this factor is. This factor is x squared, because we started off with the power of 3, and since the leading coefficient is a 2, this should be 2x squared plus 15x minus 27. Now what this means is my function f of x is x minus 4 times 2x squared plus 15x minus 27. I know that because they gave us a 0. One of the zeros is 4, and that implies x minus 4 has to be a factor. That's where the x minus 4 comes from. And from synthetic division, we have 2x squared plus 15x minus 27 is left over after we take out x minus 4. And that's negative 54. And then we'll put the 15 on the bottom. Positive 18 and negative 3. Those are the two numbers. Now we can use the bottom up technique for this. I can divide both of these by the leading coefficient. That's 2x. And then we can reduce. This is 9 over x. This one is negative 3 over 2x. You can bring the bottom to the top. And this factors this part of it. Or you could use split the middle. Whatever technique you want for this problem. We have f of x is equal to x minus 4 times x plus 9 times 2x minus 3. And there is our solution. It is factored as x minus 4 times x plus 9 times 2x minus 3. Question 13. Let's factor the polynomial given its picture. I know there is a 0 at negative 5. There's 1 at 0, and there's also one right here at 2. So we have 3 different zeros. So we can rewrite our function f of x as x plus 5, x plus 0, and x minus 2. Well, x plus 0 is just x, so we can put that in the front, and we'll have x plus 5 next, and x minus 2. Now let's look at -5. This has to have an even multiplicity because we're going to bounce off the x-axis. So the power must be even. So we need a square term here. For the 0 and for the 2, it shoots right through it, so the power should be odd. Now let's double check to make sure our exponent is a 4 when we multiply all this out. If I multiply x times this is an x squared here times x, I do get x to the 4th. So this is our function. Our function f of x is x times x plus 5 squared times x minus 2. Again, you have to look at the multiplicity. It has to have a multiplicity of 2 for the -5 because there's a bounce off the x-axis. For question 14, the idea here is to try to get the same base. The bases are different, but if you check carefully, these are both divisible by 9. So that's my target. I want the base to be the same. Let's choose 9. On the left, I can rewrite this as 9 squared raised to the 3x minus 3. On the right, I can check with my calculator. 9 cubed is indeed 729. And now we're very close to getting the same base. We just got to simplify the exponents a little bit. Let's use distribution. And this would give me 9 raised to the 6x minus 6 equals 9 raised to the 3x plus 12. Since the bases are the same, well, the tops of our exponents better be the same. So 6x minus 6 has to be equal to 3x plus 12. Let's subtract 3x to both sides. That gives me 3x minus 6 equals 12. Let's add that 6 to both sides. 3x equals 18. And now we can divide both sides by 3. X is equal to 6. Now if you're not sure, you can plug in that 6 for the x and double check with the calculator to make sure both sides are the same, and they are. In question 15, we'll be using the formula a equals p times 1 plus r over n raised to the nt. For question 15, let's find the present value that will grow to $1,000 if the annual interest is 6.5% compounded quarterly for 5 years. I am looking for the present value. That's the p. We don't know what that is, so we'll leave it as a p. And we want to end up with $1,000. That's going to be a. The r is the 6.5%, but converted to a decimal. So it's 0.065. It's compounded quarterly. That means n equals 4. And the time is 5 years. So we have everything we need. We'll just plug it into the formula above. We have 1,000 equals p. We don't know that. We're looking for it. 1 plus 0.065 over 4 raised to the 4 times 5. I can simplify this by simplifying the parentheses first. This is 1,000 equals p times 1.01625. I'm just simplifying the inside of the parentheses, and 4 times 5 is just 20. Now to solve for p, I can divide both sides by 1.01625 raised to the 20. This reduces, so we're just getting p. So we have 1,000 divided by 1.01625 raised to the 20, and we'll just type that in our calculator. And we'll round it to 2 decimal places because we're talking about money. And this gives me a value of $724.42. So we need to put that much in the account to end up with $1,000 in 5 years. For question 16, we want to expand if possible. So I'm going to use either my quotient rule, product rules, or power rules. For this problem, I like to use the power rule first. So let's rewrite this as log base 4 of a, b, c to the negative 1, d to the negative 1. All I did was I moved these numbers up here. They have an exponent of 1, so we can move it to the top, and their exponents will be negative. Then we could use the product rule. The product rule says we can multiply all this out using addition. So this is log base 4 of a plus log base 4 of b plus log base 4 of c to the negative 1 plus log base 4 of d to the negative 1. Now there's more than one way to do this. You can use different techniques, but you should still get the same answer. And then I'm going to use the power rule. This is log base 4 of a plus log base 4 of b. And this negative here, I'm just going to bring that to the front using the power rule. So that's negative log base 4 of c minus log base 4 of d. It's quite a long solution, but it's not too difficult to do. For question 17, we're going to do the opposite. We want to combine this into one big log. So I like to use the power rule. So let's rewrite this as log base a to the x plus log base a of y. I didn't do anything to the first two terms, but for the second one, there's a negative here. I like to bring that to the exponent. So this is going to be a plus log base a of t to the negative 1 now. And then we can combine all of these with the product rule. This is log base a of x, y, t to the negative 1 using the product rule. And we have to make sure this t to the negative 1 goes in the bottom. So we have this is log base a of xy over t. And this is our solution. You could also do the product rule for the first part, then do the quotient rule. You should still get the same answer. I like to work with those negative exponents because they make my life a little bit easier. But you could do this problem any way you like. Question 18, let's solve the exponential equation and of course round to the nearest thousands. For this question, I always try to get the same base, but you'll probably realize that's not possible. You cannot get the same base. But what we can do is we could take the natural log of both sides. Let's start by taking the natural log of both sides of this equation. And now we can bring that exponent to the front. Using our exponent rule, we can bring it to the front. So this is x plus 1 times the natural log of 6 equals 2x minus 1 times the natural log of 4. Now we're trying to solve for x, so we got to get the x by itself somehow. And to solve for x, I'm going to have to do distribution. So let's distribute the natural log of 6 into here. And we'll distribute the natural log of 4 into here. So this gives me the natural log of 6 times the x plus the natural log of 6 equals 2x times the natural log of 4 minus the natural log of 4. So be careful, we're multiplying natural log of 6 times x and then times the 1. Here we're multiplying the natural log of 4 times 2x and then timesing it by the negative 1. We'll get the x's on one side, so let's subtract the natural log of 6 to both sides. And I'm going to also subtract 2x natural log of 4 to both sides. So this gives me x natural log of 6 minus 2x natural log of 4 equals negative natural log of 4 minus natural log of 6. Do not feel tempted to simplify this as natural log of 10. This is not possible. Leave it as this, and we're going to solve for x. To solve for x, I'm going to factor out the x. Factor out the x. So we'll take x out, that's natural log of 6 left over, minus, if you take out the x, that's 2 natural log of 4. And that's equal to negative natural log of 4 minus natural log of 6. We're almost there. We're going to divide both sides by the natural log of 6 minus 2 natural log of 4. Again, both sides is divided by the natural log of 6 minus 2 natural log of 4. And we just need to enter this whole thing in a calculator. Be careful, I would use parentheses for the top and parentheses for the bottom. And just a precaution, you probably should put parentheses around each of these arguments so you don't make a mistake. And this gives me a value of 3.240 approximately. So double check with your calculator. I always put many parentheses just to make sure. So I'm going to put a parentheses here, minus natural log of 4. I put a parentheses for that, minus natural log of 6. Put a parentheses around that. Then close it off here. Then divide by another parentheses here. And then I need to make sure I have a parentheses at the end as well. So make sure you get 3.240. That's the correct answer. For question 9, recall log base b of x equals y is the same as b to the y equals x. So I can rewrite this as 6 raised to 2 equals 5x minus 1. Now 6 squared we know is 36, and that's equal to 5x minus 1. Let's add the 1 to both sides. We have 37 equals 5x. And now I can divide both sides by 5. And our solution is x equals 37 over 5. But you want to double check, right? You want to make sure this is right. So plug it into the x and make sure we do get the 2 when we evaluate this log. So let's check to make sure. That's log base 6 of 5 times 37 over 5 minus 1. Is that equal to 2? This is log base 6 of 36. Is that equal to 2? Yes, it is. 6 squared does give me 36, so this checks out. It works. Question 20. We have log x plus log of x minus 15 equals 2. I'm going to use the product rule for the first two here. This is log of x times x minus 15, and that should be equal to 2. We can distribute the x now. This simplifies as log x squared minus 15x, and that's equal to 2. Now it's going to be difficult to get rid of this log unless you know what the base is. Since the base is not there, we know it's a base of 10. So I can rewrite this as 10 squared equals x squared minus 15x. We know 10 squared is 100. And now I can solve for x. Let's subtract 100 on both sides. I get x squared minus 15x minus 100 is equal to 0. This factors as x minus 20 times x plus 5 equals to 0. And so we have two potential solutions. X could be equal to 20 or x could be equal to negative 5. But you have to double check to make sure these are good solutions. You have to double check to make sure these are good solutions. So plug in x equals 20 and plug in x equals negative 5 into the equation. I'll check the first one. Log of 20 plus log of 20 minus 15. Is that equal to 2? That's log of 20 plus log of 5. Is that equal to 2? I could use the product rule. This is log of 100 equals 2. That's correct. So we know 20 is a good solution. Now I gotta check negative 5. Log of negative 5 plus log of negative 5 minus 15 equals 2. And right away we have a problem. We have a problem because there's a negative on the inside. You cannot take the log of a negative. So that means negative 5 is a bad solution. We only got one good solution. That's x equals 20.